Okay, for our next section, section 11.2, we're going to be looking at a new type of function. And in 11.2, our focus will actually be what we call exponential functions. We have seen many different types of functions, and depending upon what you're doing with the variable x, that determines the nature of your function. If we had just a 3x, that's linear functions. If we have an x squared, then that's when we called it a quadratic function. If the x is in the denominator of a fraction, that's when we called it a rational function. If the variable x was found underneath a radical, of course, that's when we called those functions radical functions. Well, in order for a function to be considered an exponential function, what we have is f of x equaling a, some value of a, to the power of x. So with exponential functions, x, the variable, the input, the domain, is actually your exponent. And so what we're going to consider here is a is going to be some number greater than 0. Any number greater than 0, of course, except the number 1. The base a will never be the number 1, but it must be a number greater than 0. That means it could be any fraction or any other number greater than 1. And the variable x is going to actually be a real number. For example, we might have f of x equals 2 to the x power. That would be an example of an exponential function. Or we might have g of x equals, let's say, the fraction 1/2 to the x power. In both of these cases, what we have here are two examples of exponential functions, because a is a number that is in fact greater than 0 and not 1, and the variable x will be any real number. And what we want to do, first of all, with these exponential functions is we want to graph them. We want to see what the graphs of these two exponential functions are going to look like, provided we put them on the coordinate plane. And let's graph each one independently. For starters, let's graph the function f of x equals 2 to the x power. And when we make a graph, what we're going to do is we are going to create a table of values, x and f of x. And we're going to try to come up with, I would say, 5 values of x. And then we will substitute them into our function. And what's nice about exponential functions, in terms of the domain, we will be able to see that the domain is all real numbers. We will be able to plug in any value, any real number for x. So for example, I am going to substitute values of x such as -2, -1, 0, 1, and 2. And we will always use those same values of x. And now what we have to do as far as our function is concerned is we want to take the base 2 and raise it to the different powers. And you could use a calculator to help you out with this. So for example, if you take 2 and raise it to the -2 power, your calculator would tell you 1/4. If you were to take the value of 2, that base 2, and raise it to the -1 power, we would of course get the fraction 1/2. 2 to the 0 power is 1. 2 to the first, of course, would be 2. And of course, 2 squared, 2 to the second power is the number 4. And what we're going to do now is we will take this table, and from the table we will create a coordinate plane. So let's start by just plotting a few points, and based upon those points, we will construct our graph. Actually, let's go with a different scale. That seemed a bit small. is a little bit better. So when x is a -2, we will have to approximate the y value of 1/4. That would probably be about over here. When x is a -1, y would be 1/2. When x is 0, y is 1. When x is 1, y is 2. When x is 2, y is 4. And when you connect these dots, you wouldn't actually use a ruler to connect them because it's not going to form a straight line. There's a curve to it here, okay? So we can see here in terms of the domain is all real numbers. If we were to talk about, let's say, the range of this function, for that we want to look at the y values. The range is that it's going from 0 to infinity. It'll never actually hit 0 as far as y value is concerned. You'll notice that the y values will just get smaller and smaller and smaller and approach 0, but never actually getting there. We will definitely have a y-intercept located at 0, 1, and we can see that right here on the graph. As far as our x-intercepts are concerned, there aren't any. Nowhere will this line ever cross or touch the x-axis. And you'll notice here that this line keeps growing. It grows up and up and up towards that positive infinity. And we would say here, because your a value is a number greater than 1, this is what's called an exponential growth. Because your y values are going to continue to grow in a rapid way. As x grows, so will y, okay? And that's why we're going to consider this an exponential growth. Let's take a look at the graph of the second function, g of x. In g of x, now we have this 1/2 to the x power. And once again, I'm going to use the same exact table, x and g of x. And once again, I'm going to come up with 5 values of x. And we always use the same 5 values, -2, -1, 0, 1, and 2. And because, once again, we know the domain is going to be all real numbers, that's why we could pick those values of x. And if you were to take that base 1/2 and raise it to these different powers, let's see what we would get. Well, 1/2 to the -2 power would actually give us a +4. If we were to take the base 1/2 and raise it to the -1 power, we would get a +2. Just like before, when we take 1/2 and raise it to the 0 power, we get 1. 1/2 to the first power would be 1/2. And lastly, if you take 1/2 and square it, you would get 1/4. And now let's see, when we go to our coordinate plane, what will this do? What will it form in terms of our graph? So we're going to plot points at -2, 4. Then we'll need to put another dot at -1, 2. Our third dot will be located at 0, 1. We will have to approximate the dot at 1, 1/2. And then lastly, we'll have to approximate the ordered pair for 2, 1/4. And when we connect these dots, we have a similar looking graph in that in terms of the range, once again, we are going from 0 to infinity. We will approach 0 from the y-axis, and we're going to go towards a positive infinity. In terms of the y-intercept, it's the same as before. It's located at 0, 1. And since this curve will never ever touch the x-axis, once again, in terms of the x-intercept, we would be able to say that there is none. Now, if we were to look at the two graphs, And here we called this an exponential growth because the values of y continue to grow. Well, let's take a look here at what's happening in terms of this exponential function. Here we have a value that is somewhere between 0 and 1. It's a fraction. It's still positive. It's still not 1. It's a number between 0 and 1. And when that happens, when your base number is a number between 0 and 1, what we have now is considered an exponential, not growth, but decay. That's the major difference between the two graphs. It all depends upon what your a value is. In the first one, our a value was greater than 1. That's why it was an exponential growth. In our second example, the a value was a number between 0 and 1, and when that happens, we have an exponential decay. So those are your exponential functions. What we want to talk about now, the other part that we have to address in section 11.2, is solving a different kind of equation. We are going to take a look at solving exponential equations. Now, in order for us to solve exponential equations, we need a property of equality. That's what will help us solve exponential equations, is the property of equality. And the property of equality tells us something like this. If b, once again, is a number greater than 0, and as long as it's not equal to the number 1, b to the x sub 1 power will equal b to the x sub 2 power if and only if, and right here is the abbreviation for if and only if, x sub 1 is going to equal x sub 2. So this is the property of equality that we're going to use to solve exponential equations. The property of equality tells us if our base number is a number greater than 0, has to be a positive number, and not equal to the number 1, then b to the x sub 1 power is going to equal the same base to the x sub 2 power if and only if x sub 1 equals x sub 2. Let's take a look at how we can use this property of equality to solve exponential equations. For example, let's say we have 5 to the 2x plus 1 power is going to equal to, let's say, 5 to the x plus 3 power. Now, here we have an exponential equation. Why is it considered an exponential equation? Because the variable x is located in the exponent. And because we have base 5 raised to the 2x plus 1 power equals base 5 raised to the x plus 3 power, well, let's take a look and see if this property of equality can be used. Let's look at our bases first of all. The number is 5, and since the number 5 is a number greater than 0 and it's not equal to the number 1, what we'll be able to say is that 2x plus 1 has to equal an x plus 3. So now what we have done is we have turned this into a linear equation. By getting rid of those bases now, because the bases are the same number, numbers that are greater than 0 and not 1, we'll be able to now just ignore those bases and work with the exponents, because that's what the property of equality tells us. So if 2x plus 1 equals x plus 3, and now we want to solve for x, I'm going to subtract the x over. That would give me x plus 1 equals 3. And if I subtract the 1 over now, we would get, of course, x equals the number 2. And that would be your solution. X equals 2 is the solution to our very first exponential equation. Once again, we used the property of equality. Let's try another one. Let's say we had the number 6 raised to maybe the 3x minus 5 power equals 6 raised to, let's say, the 5x plus 6 power. Once again, our property of equality, as long as our base numbers, which are here now are 6, okay, these numbers are positive, they are not equal to the number 1, and according to our property of equality, if these bases are equal, that means the exponent of 3x minus 5 has to equal the exponent of 5x plus 6. Once again, creating now a linear equation. And if we want to solve this for x, I'm going to subtract the 3x over, as well as I'll subtract the 6 over, giving us now a negative 11 equals a positive 2x. And now to solve for x, you'd have to divide both sides by 2, in which case we would get x equals a negative 11 halves. That would be your solution to that exponential equation. Okay? That's using, once again, the property of equality. Now, those were relatively easy, okay, because the bases right off the bat were in fact the same number, okay? We had a base 5 here, we had a base 5 on the right side as well. On the left side we had base 6, on the right side we also had base 6. Okay, that's the way we like it. But what if we had something a little bit different? Let's say, for example, we had 2 to the, let's say, 2x plus 1 power equals the number 8. Well, here the problem is a little bit different because we don't have the same base on either side of the equation. We have base 2 on the left side, and we have base 8 on the right side. And that means we can't use our property of equality just yet. But what we're going to have to do is change one of the bases, because we need to have the same base on the left and on the right. And it's going to be easier to take the larger number and write it as the smaller base. So we are going to leave the left side as 2 to the 2x plus 1 power. However, now let's take a look at the number 8. Let's see, is there a way of taking the number 8 and writing it as a base 2 number? 2 to what power would give me the number 8? And of course, we should know that 2 to the third power is the same thing as 8. So we are not changing the value of the equation. We are just rewriting it in a more familiar form, okay, where we can have the same base. And since now we have the same base on both sides, and those bases are positive and not the number 1, we can now forget about the bases and simply state that the exponent on the left of 2x plus 1 has to equal the exponent on the right, the number 3. And so now we can solve this linear equation. I'll subtract the 1 over, and that would give us 2x equals 2. And when you divide both sides by 2, we get x equals the number 1. And that would be the solution to that exponential equation. So you want to look carefully at both bases initially. You want to make sure that they are, in fact, the same number. Let's try another. similar to the one that we just did. Let's say we have 9 raised to the x plus 3 power equals 3 to the 3x power. Now, once again, let's take a look at this equation, particularly for starters, the bases. I have base 9 and I have base 3. They are both positive numbers and not 1. However, they are different bases. So just like we did in the previous problem, we're going to take the larger number 9 and we're going to see if we can write it as a smaller base number, base 3. So let's think about that number 9. 9 is the same thing. This number 9 here is the same thing as 3 squared. And that's still going to be raised to the x plus 3 power equals, now the right side we don't have to do anything with. I'm going to leave it as 3 to the 3x power. Okay, now let's see what we can do. On the left side, I do need to simplify. Way back, I believe it was in chapter 5 maybe, where we were talking about the laws of exponents. And the laws of exponents told us that if we have a power raised to another power, we actually have to multiply the powers. So now the equation would read 3 raised to the 2x plus 6 power, because don't forget you have to distribute that 2 on those two terms, is going to equal 3 to the 3x power. And now let's see what we have going on here. We have the same base number. They are positive numbers and not the number 1. And since they are fulfilling that criteria, we can just work with our exponents, in which case now 2x plus 6 would have to equal the 3x. Now once again we want to solve for x, so I'm going to subtract the 2x over, in which case now we would get x equals the number 6. Let's try another. Let's say we had the following. We might have, let's say, the number 9 raised to the 6x power equals 27 raised to the x minus 4 power. Now once again, we are looking to see that we need to have the same base numbers on the left side of the equation and on the right side of the equation. And if we give a lot of thought to these two numbers, we can write both of them, both the number 9 and the number 27, as base 3 numbers. We know that 9 is the same thing as 3 squared, which is still being raised to the 6x power, and 27 is the same thing as 3 cubed, and that is raised to the x minus 4 power. Now, just like we did in the previous example, when we have a power raised to another power, we have to multiply those powers. So that would now give me, on the left side of my equation, 3 to the 12x power equals, here on the right side, I'm going to have to go and distribute that power, in which case now I have 3 to the 3x minus 12 power. And so now we have the same base numbers on left and right side of the equation. They are positive numbers and not equal to the number 1, in which case now we can go and take the exponent of 12x and set it equal to the exponent of 3x minus 12. Okay, once we have the same base, we no longer need the base, and we're going to work simply with our exponent, because that's what the property of equality tells us we can do. Now we want to solve this for x, so let's subtract 3x from both sides. On the left side, 12 minus 3 would give us a 9x equals a negative 12. And now to solve for x, we'd have to divide both sides by 9, in which case we get x equals, let's simplify this fraction, and it would simplify to a negative 4/3 as our solution. Let's try a harder one. For example, let's say we had maybe 4 raised to the x minus 5 power is going to equal, let's say, the fraction 1/16. Okay, now it starts to get a little interesting. Well, once again, we want to work with the same base. Let's work with the smaller base. So I'm going to leave the left side alone. I'm going to keep it as 4 raised to the x minus 5 power. But this 1/16, I'm going to leave the 1. However, 16, that's the same thing as 4 squared. So 1/16 is the same thing as 1 over 4 squared, because 4 squared is 16. Now, what else can we do? Let's take a look at both sides of this equation. On the left side, the 4 is in the numerator. On the right side, the 4 is in the denominator. And we can't have that. We need the base of 4 to be in the same location. So I'm going to leave the left side alone. I'm going to leave it as 4 to the x minus 5 power. The right side, however, we had a law of exponents involving negative powers. You may recall a to the negative m equals 1 over a to the m. So we're going to use this idea in that instead of 1 over 4 squared, that would be the same thing as 4 to the negative 2 power. These are equivalent. 1 over 4 squared and 4 to the negative 2 power, they mean the same thing. Except now we have the same base. It is a positive base, and it's not the number 1, in which case we no longer even need to worry about the bases. We're going to take the exponent of x minus 5, and we're going to set it equal to the exponent of negative 2, in which case now we want to solve for x. So I'm going to add that 5 over, giving us a solution of x equals to the number 3. Okay? So when solving exponential equations, you may have to manipulate one or both sides to get a common base. Remember, look at your numbers. Always take the bigger number and try to rewrite it as a smaller base number. Okay? Your ability to think of numbers in different ways will come in handy here. You want to be able to manipulate those numbers to create equivalent other numbers. Okay? Like we did, 16 is the same thing as 4 squared. 27 is the same thing as 3 cubed. Okay? All depending upon what the base number is, that will determine what exponent you're going to have to raise it to. Okay? That completes section 11.2. There is some homework that goes along with this. Give it a shot and shoot me any emails that you may have with any questions or concerns. Be well.